Welcome back, class. This video, we are going to be going over the notes that we started in class today. We went over the top example. I'm going to redo that for you, and then I'm going to go over the bottom example so that you get a better idea how these problems work. The first thing I want to note is that the function given is f of x. That's not something you're supposed to figure out. I should have put it in the graph. I should have told you it was f of x. But since I didn't, will you please add f of x so you know that this is the graph of that function. Now, right next to it, you're going to notice a graph of, they're going to define g of x. I'm just going to kind of box it in right here. G of x is defined as the integral from 1 to x of the function f of t dt. And remember that we are just using a dummy variable here, t, but in reality, they're referring to the function f of x. And so the first problem says to compute g of 2. So if I were to plug in g of 2 in here, see? I would, just like regular evaluating functions, I would plug in a 2 for the x, so that gives me the integral from 1 to 2 of f of t, or in this case f of x dx. Since I've now replaced the x with 2, I can use my x again. And so what this means is that I'm going to compute the net area starting at 1. So my starting point here is at 1. I'm just going to put a dotted line to remind me of that. And then I'm going to go in the direction of 2. Okay, now, if you remember, net area has a sign. It's either positive or negative, and it depends on the location and direction. If I'm moving to the right and I'm located above, all of this area will be positive, including this little triangle here. But if I am below and moving to the right, I have a positive situation and a negative situation. The positive is the direction, but the negative is the location. Then I end up with a negative result. Likewise, if I move to the left here and I'm located above, this entire area, this triangle here, is going to be negative. So going back to the problem at hand, we're going to find the net area from 1 to 2. So I'm going to seal it off here. And that does create a really nice trapezoid where the height is the distance between the two parallel sides. So it's going to be 1/2 my height. Times the sum of the bases, and the first base is 4 and the second base is 1, so that's a 5, and so that ends up being 5/2 or 2.5. Okay, so that's how you evaluate the first one. I'm going to go ahead and ask you to pause the video and compute g of 4 and g of -2. If you've done that already, you can compare your answers to mine. I got 2.5 for both g of 2 and g of 4, and then -6 for g of -2. So let's move on to the next question. In the next question, we are being asked to find the derivative of g at 2. The derivative of g at 2. Okay, well, I know that g of x is an integral, so I basically have to take the derivative here of both sides. And so what that means is that g prime of x here is going to equal the derivative. I'm going to do this the long way first. So I'm going to take the derivative of the integral from 1 to x of f of t dt. And we've been doing this now. The fundamental theorem of calculus, part 1, says that the derivative and the integral are inverses, which basically means they cancel. I get to plug in my x, and the result is f of x. So that means that g prime of x equals f of x. And I know that you're used to thinking of slope of tangent lines for the derivative, but because of the way g is defined, its derivative is going to be the function f, meaning these y values represent the derivative of g. So if we want g prime of 2, we're really looking for f of 2. So at x equals 2, the y value that corresponds to that is 1. So the answer is 1. Okay? You can stop the video and go ahead and compute g of 1 and then compare to my answers. So you see we have, I found g prime of 1 to be 4, which is going to be the y value at x equals 1. Now the next question asks for an equation of a tangent line. Equations of tangent lines require two things. They require a point and they require a slope. So if it's the equation of a tangent line to G at 2, I know that my x coordinate is going to be 2, and I do need to find the y, and I also need to find the slope, and the slope is going to be given by the derivative of G at that specific point. Well, the derivative of G at that point we found earlier, right here, it's going to be 1, so I already know that information. And I also know that the y value is going to be given by G of 2. G of 2 is 2.5. So I can go to my point-slope form and just fill in the blanks. And I do not have to solve for y unless it's a multiple choice question that requires me to do so. But this is good enough. Here's my one slope. So there's my equation of my tangent line. The next example asks us to figure out where g of x is increasing. Well, if you remember from the last unit, g of x is going to be increasing when the derivative is positive or greater than 0. Well, since we know that the derivative of g is equal to the function f, what we're really looking for is where is f positive? Where is it above the x-axis? And I'm just going to take a moment and erase this stuff here so we can see things a little bit more clearly. So I want to know when f of x is positive. That means I'm not looking at a slope on f. I'm looking at where f is above the x-axis, which happens starting at -2, and it stays positive. Even if it's decreasing, the y values are positive until 3. Now, because it's increasing, I will accept bracket or parenthesis, but I do note that the derivative here is 0. So I'll go -2 to 3. Okay. If they asked us about decreasing, we are below the x-axis. That would have happened from 3 to 4. Next question. Where is the graph of g concave up? Well, if you remember, concave up simply means g double prime is going to be greater than 0 for up, less than 0 for down. Well, if we go back to our statement that g prime of x is equal to f of x, we're going to need to go to the second derivative. So just imagine taking the derivative of both sides. That's going to give us g double prime of x will then equal f prime of x. And we need to figure when that is going to be positive. Well, f prime is actually slopes of tangent lines. So while in this case, we were looking at y values. Let me write that down. So for this part, we were looking at y values. In this part, we're now going to be looking at the slope of the graph. And so if you take a look at the slope, we're looking when that slope is positive, and that happens from -2 all the way to 1. And so I'm going to put that in parentheses because concavity is always given in parentheses. And then from 1 to 4, you see that it's decreasing. Even at this point, there's a corner, but it continues to decrease. So direction never switches. It does ask about inflection points. If you recall, inflection points are the points where concavity on the original graph changes. For the second derivative, all we have to do is check that it changes sign from positive to negative or vice versa. So you'll note that because we're given f, g double prime is the derivative. So what we really need to find is when f prime is going to change sign. And that means we're going to take a look at the slope and determine when the slope changes sign or direction. So you see here I'm going up and now going down. So at x equals 1, that must be an inflection point. And you ask yourself, well, there's no concavity on this graph. True, but the question is about concavity of g. We're just using the graph of f because that's how g is defined as the net area under the f curve. So that's why it's 1. Here it is not an inflection point because although it is a corner, the function is decreasing and decreasing. So really the slope never changed signs. Now the last question is a little tricky in some respects. And there's 2 ways to think about it, and I'm going to explain both ways. They want to know the minimum value of g of x. Well, ultimately, g of x is the net area under the f curve. So we're going to take a look and say, all right, if I start at 1, and if I move to the right, all of this area is going to be positive. So it's going to be positive all the way to 3. But as soon as I get to 3, I go below, and now that's negative. So I'm going to have more positive area at 3 than I would all the way to 4. Okay? Now, if I go backwards to -2, all of this we said was negative. So clearly, 3 is going to have the biggest value. So I'll just put x equals 3. And then the maximum value, well, oops, I've totally flipped that around. Sorry. X equals 3 is the most positive area, so that should be the maximum value. The minimum value is going to happen at -2 because that's where we're going to get the most negative area. We do have a little bit of negative area here, but if you combine it with the positive area, that's not going to be enough to beat the amount of negative area at -2. So x equals -2. Okay? Another way to think of this is using the method that we use for finding extrema when the interval was closed. If you remember, what we did back then is we made a table of values, and we said that we would consider any endpoint, so -2 and +4, and then any critical point in between. And the critical point is when the derivative, in this case f of x, will equal 0. So if you go look for whenever f of x is 0, well, that's -2, but that happens to be an endpoint, so that's not a critical point. And then we have 3, and then we have 4. Okay? Now, I believe we already evaluated g of 4, so g of 4 is 2.5. We also evaluated g of -2, so that's -6. And I don't think we ever did g of 3. So let's go ahead and do that right now. We evaluated g of 2, I know. G of 2 was 2.5, so this area here is 2.5. And I'm going to go ahead and add this triangle. It's 1/2 base times height. So that's height is 1, base is 1, so that's going to end up being 1/2. So if I add 1/2, that gives me 3. So if I just look at this table, the lowest y value comes at -2. So that's my absolute min. And my highest y value comes at 4. Nope, let me say that again. Comes at 3. That's my absolute max. So 2 ways to think about it. This is just by literally looking at the graph and thinking about it logically. This is systematic, and it's how we used to do extrema in a closed interval. Okay? In a closed interval. Alright, I'm going to put the other example on a second video so that it doesn't get too long. But hope this helps. See you on the next one.